I want to continue our discussion of relations in algebra today, and specifically talking about how can you recognize whether a pattern is linear or not. Remember that there's many ways to represent a relation. We can do so with an equation, which is what I have here. We can also turn that relation into a table of values, into a graph. We can even say the relation in words. In this case, it would be to take our independent variable x, take any number x, multiply by negative 2/3, add 1 onto that, and we get our dependent variable y. Y depending on what we choose for x. So the big question I want you to keep in mind as we go through this, can you recognize whether a relation is linear or not based on the equation, based on the table, and based on the graph? The graph, of course, will mean we get a line, so that's a bit more obvious. But can you determine or recognize a relation as linear from the equation and the table of values? So let's take our relation and build a table of values. Our independent variables on the left. We can take any value of x. It's independent of anything. So let's choose x equals 0, and we plug 0 in for x in our equation. Negative 2/3 times 0 is 0 plus 1 gives me a y value of 1. And let's start building our graph as we go. So 0, 1 is kind of like our starting point. If x was nothing, we'd be starting off with a y value of 1. Alright, now we can take any value of x, as I said. X equals 1, x equals 2. I'm going to actually jump to x equals 3 because that will be an easier value to work out. And if you're wondering why I'm doing that, you'll notice that I have a fraction that I have to multiply by. So I'm going to choose a number in which I can cross cancel the 3 easily. So I'm going to choose x equals 3 because when I cross reduce, those go away, and I'm left with negative 2 times 1, negative 2, plus 1, which is negative 1. And so I've got another point on my relation, which I can graph. I'm going to choose another value of x that's easy to multiply by negative 2/3. I'm going to choose 6 because that will cross reduce nicely. So x equals 6. If I cross reduce, negative 2 times 2 is negative 4 plus 1 is negative 3. Okay, and let's go one more time with 9. Negative 2/3 times 9. Again, choosing 9 because it's a multiple of 3, and cross-reducing will allow me to get more convenient numbers. Negative 2 times 3 is negative 6, plus 1 is negative 5. Okay, and I can plot those last 2 points that I found. 1's there, and the 9's a little off the grid. It's going to be right there. You can see my points are lining up, so this is looking like it's linear. Let's just find a few more values for our table. Let's do a negative 3x value. So in we substitute it. Negative 2/3 times negative 3, which is negative 3 over 1, plus 1 will give us our y value. Cross reduce. Negative 2 times negative 1 is 2, plus 1 is 3. So we can plot that point. And again, it's lining up. So we can definitely tell that our relation is linear from the graph. Is there anything we can see in our table that might tell us that the relation is linear? You'll notice that if I go down my x column, my x values are increasing by 3, and at the same time, my y values are decreasing constantly by 2. That is a key feature of linear relations. Specifically, and I have it written here, a constant change in one quantity, so a constant change in our x produces a constant change in our other quantity, y. Our change in y, we said from the table, was going down by 2, so I'm going to say negative 2 for that. And our change in x was a change of 3 as our y was changing by 2. And that's how you can recognize a linear relation. There's a constant change in y for a constant change in x. So I could actually use this information to my advantage to get a couple of more points. If I were to back my table up to -6, then because the pattern in both is constant, this should be 5. And I get my point right there. And it's linear, so what I'm going to do is I'm going to join the points with a solid line. Now the reason I'm joining the points with a solid line, let's put arrows on the end, is to show that any point on this line is part of this relation. If I had chosen, for example, remember how I avoided choosing x equals 1 for my table. If I had chosen x equals 1, let me just substitute it in over here, -2/3 times 1 plus 1 to get y. That would have been -2/3 plus 1, and 1 is 3/3. That would have given me a y value of 1/3. And so the point 1, 1/3, which is right here, you'll notice that it's part of my line. So my table gives me a sampling of the points that satisfy the relation, that are part of the relation. I join with a solid line to show that all points in that pattern are part of this relation, because it's not possible for me to find every single point in my table. So we've answered the question, how do you recognize a relation as linear? By looking at the table of values, by looking for a constant change in y with a corresponding constant change in x. In terms of this rate of change, by the way, you can also see it on the graph. If I go from this point here and I change y 2 and go over 3, I get to the next point. I drop 2 y's and I increase 3 x's, I get to the next point. You can see how that produces a line when you keep going in that rate of change from point to point. What about the equation? How do you tell whether a relation is linear by looking at its equation? Well, a linear relation is always what we call a first degree equation. And what that means is that the highest exponent on any variable is 1. So you'll notice that I have y to the 1, x to the 1. A relation of that nature will always produce a linear relation. Another way to look at that is that the most complex operations you can get in an equation that's linear is multiplication of two things with adding or subtracting a number. That's the key identifier of a linear relation. The other thing that some of you might wonder about is that in the equation we see -2/3, which, remember, related to our rate of change of y over change in x. And indeed, this is the rate of change of the graph. Change in y. The triangle, by the way, is the Greek letter delta. Change in y is shorthand for change in y over change in x. If the y is by itself in your linear relation, then the coefficient of the x will, in fact, always be the rate of change of the graph. The 1, you might wonder, does the 1 have any significance? We talked earlier about how when x was nothing, y was 1. You can kind of think of your 1 as your starting value. If x was nothing, y would be 1 in this case. Here's a problem. And it says that the cost of operating a car is $80 for fixed costs. Fixed costs are things like insurance, maintenance, repairs, depreciation, that kind of thing. And the cost is also related to how far you drive it, 40 cents per kilometer. All right, so we want to write an equation that relates the total cost for operating the car and the distance traveled for the week. All right. Some of you may be able to do this straight up, but let me just try to connect a number of things together. So if I were to put this in table of values form, my independent variable is distance, And cost is the dependent because the cost depends on the number of kilometers driven, not the other way around. So if I think of some numbers that would satisfy this relation, if I didn't drive the car at all, drove it 0 kilometers, my cost is going to be $80. That's kind of like my starting cost, my fixed cost. Every kilometer I go after that, 1 kilometer, I'm going to add 40 cents. So to drive it 1 kilometer in a week, it's going to cost me $80.40. 2 kilometers, another 40 cents. 3 kilometers, another 40 cents. So we have a relationship here between cost and distance, and the question is it linear? Well, if we look at the table, yes it is, because as we change the distance by 1 kilometer, so our change in distance, our change in cost is 40 cents. We're increasing by 40 cents constantly for every 1 kilometer change in distance. There's a constant rate of change on both the independent and the dependent variable. That's what a linear relation is. Now I could graph that and I would get a line. In terms of the equation, the cost is going to be, we're going to start with our fixed amount, 80 cents. This is our fixed amount, and we are going to add the change, which is going to be 40 cents per kilometer, so times the number of kilometers. And we have our relation given in words, given in table, now given as an equation. And you can see that the coefficient of the independent variable is the rate of change, and the number added on to the end is the fixed amount, which lines up with what we talked about in our last example. Finally, the reason we like to generalize into an equation often is because we can then do more complex calculations with the equation. So for example, let's use our equation to calculate the number of kilometers driven in a week if we know the cost to operate the vehicle was $210. Since we know the relationship between distance and cost, what I could do is I could substitute 210 in for cost, and that would give me the distance that goes along with that given cost. So I can subtract 80 on both sides. Divide both sides by 0.4. And what this is telling me, that's 325. So what this is telling me is that if I drive 325 kilometers, it's going to cost me $210.